Fourth procedure, measure how far the block moves. Then, record this as the stopping distance. For this activity, the direction, fill in the box. Initial distance, centimeter, then stopping distance, centimeter, of the small toy car. Then lastly, the stopping distance, centimeter, of the big toy car. After that, repeat steps 3 and 4 while varying only the initial position, distance for 40 cm, 60 cm, 80 cm. Lastly, do steps number 3 to 5, this time using the bigger toy vehicle. Record your data in the table. How will you compare their stopping distances? For the guide questions, first, how will you compare their stopping distance? Second, did the two toy car immediately stop as they hit the block of wood? Describe the stopping distances of the two toy cars as their point of release increases. Third, what do you think happens to the velocity of the two toy cars as the point of releases increases? Fourth guide question, if momentum is a measure of how difficult it is to stop a moving object, which of the two cars had a greater momentum for the same point of releases? And lastly, how will it be possible for the two bodies of different masses to have equal momentum?
For the second activity, catching the egg.
For activity number 2, direction, identify the factors that affect the time of impact of moving objects. The materials needed, 1 raw egg, clear plastic bag where an egg can be inserted, piece of cloth, or a large handkerchief. Procedure, first, look for an open space in your school where you can perform this activity. Second, place the raw egg inside a clear plastic bag and tie the plastic bag securely. This is needed to prevent the egg contents from splattering in case the egg breaks. Third, have a companion. It's either your friend, brother, or sister. Stand 3 meters away from each other. Each pair should have 1 large handkerchief or bandana. Fourth, the objective of the game is to have the eggs travel back and forth from each other without breaking the egg. The players are only allowed to throw the egg in a curved path. Fifth, you are not allowed to use your hands in throwing and catching the egg. Instead, you will use the cloth or handkerchief. 6. Increase the distance by 1 meter between the two teams in order to make the game more interesting and challenging. And lastly, the pair who is able to catch and throw the most number of eggs without breaking would be declared as the winner. Answer the following question. First question, was the handkerchief able to protect the egg from breaking? Second, did the egg break immediately when it hit the ground? Third, how was the impact force lessened by the use of the handkerchief?
To deepen our understanding on this lesson, let's do this activity.
Deepen. Given the following data, solve for momentum using the formula P equals mv or momentum equals mass times velocity. Complete the table by finding the momentum of the bird if the mass is 0.03 kg and the velocity is 18 meters per second. Another, find the momentum of basketball player if the mass is 100 kg and its velocity is 5 meters per second. Find the momentum of bullet if the mass is 0.004 kilogram and its velocity is 600 meter per second. Baseball, if the mass is 0.14 kilogram and its velocity is 30 meter per second. Lastly, find the momentum of frog if the mass is 0.9 kilogram and its velocity is 12 meter per second. After completing the table, answer the following problems. For number 1, how much force is applied during a 0.30 second 210 Newton-second impulse? For number 2, how much force is required to stop a 0.145 kilogram baseball traveling at 44 meter per second in 0.020 seconds? For our Jumpstart activity, read each clue and fill in the appropriate answer in the corresponding space. Do not use spaces in your answer. Across, for number 2, refers to the quantity of motion that an object has. 5. The energy that it possesses due to its motion. 7. Refers to distance or quantity. 9. The change in the total kinetic energy of the system. Down. Number 1. The strength to do any kind of physical activity. 3. The change in momentum produced by the force. 4. A quantity that has both magnitude and direction. 6. Refers to something which doesn't change. 8. The factors that cause an object move. 10. A collision in which linear momentum is conserved.
These skaters are racing each other at Newton's skate park. The first skater in line, the one on the left, is distracted by something he sees. He starts to slow down without realizing it. The skater behind him isn't paying attention and keeps skating at the same speed. Can you guess what happens next? Correct. Skater 2 runs into skater 1.
Conserving momentum. When skater 2 runs into skater 1, he's going faster than skater 1, so he has more momentum. Momentum is a property of a moving object that makes it hard to stop. It's a product of the object's mass and velocity. At the moment of the collision, skater 2 transfers some of his momentum to skater 1, who shoots forward when skater 2 runs into him. Whenever an action and reaction such as this occur, momentum is transferred from one object to other. However, the combined momentum of the objects remains the same. In other words, momentum is conserved. This is the law of conservation of momentum.
This figure shows how momentum is conserved in the two colliding skaters. The total momentum is the same after the collision as it was before. However, after the collision, skater 1 has more momentum and skater 2 has less momentum than before. What if the two skaters have a head-on collision? Do you think momentum is conserved then? Correct. As in all actions and reactions, momentum is also conserved in head-on collision. So, what is the principle of conservation of momentum?
In physics, the term conservation refers to something which doesn't change. This means that the variable in an equation which represents a conserved quantity, is constant over time. It has the same value both before and after an event. There are many conserved quantities in physics. They are often remarkably useful for making predictions in what would otherwise be very complicated situations. In mechanics, there are three fundamental quantities which are conserved. These are momentum, energy, and angular momentum. Conservation of momentum is mostly used for describing collisions between objects. Just as with the other conservation principles, there is a catch. Conservation of momentum applies only to an isolated system of objects. In this case, an isolated system is one that is not acted on by force external to the system. There is no external impulse. What this means in the practical example of a collision between two objects is that we need to include both objects and anything else that applies a force to any of the objects for any length of time in the system.
So why is momentum conserved?
Conservation of momentum is actually a direct consequence of Newton's third law. Consider a collision between two objects, object A and object B. When the two objects collide, there is a force of A due to B times time of A due to B. But because of Newton's third law, there is an equal force in the opposite direction. On force of B due to A times time of B due to A. The forces act between the objects when they are in contact. The length of time for which the objects are in contact. Time on A due to B and time on B due to A depends on the specifics of the situation. For example, it would be longer for two squishy balls than for two billiard balls. However, the time must be equal for the both balls. Time of A due to B equals time on B due to A. Consequently, the impulse experienced by objects A and B must be equal in magnitude and opposite in direction. Force of A due to B times time of A due to B is equals negative force of B due to A times time of B due to A. If we recall that impulse is equivalent to change in momentum, it follows that the change in momenta of the objects is equal, but in the opposite directions. This can be equivalently expressed as the sum of the change in momenta being zero. So the first equation is mass of A times change in velocity of A is equals negative mass of B times change in velocity of B. The second equation is mass of A times change in velocity of A equals mass of B times change in velocity of B equals to 0.
To intensify your understanding of the topic, do these following activities. For your first activity, balloon rocket.